Okay, good afternoon, everyone. So the next 5 minutes that I'm going to talk about is not so much about my startup that is in its founding stages, but it's about the role systems faculty, computer systems faculty can play in a deep tech startup in a specific domain, artificial intelligence and machine learning. And so typically whenever people refer to AI and ML, the first thing that comes to our mind is algorithms and applications, because this is an area where you can relate to the Indian market and immediately see impact. But then what happens behind the scenes is also a lot of computer systems research, which in some ways has been responsible, for example, for the breakthroughs and the successes in deep learning. So it is opportunities in this area that I'm going to highlight and see sort of what role students or faculty members can play here. So compiler infrastructure for AI and ML. So compilers is the area that I work in, and it's also the area in which my startup is being founded. If we go to the beginnings, right? In the early days, people used to build compilers. You had a new language, and then let's say the company had hardware, and they used to build a compiler for that language and for that specific hardware. And very quickly, you can see that this approach has issues in scaling. If you have, for every language and for every target, you would build a new compiler. And so if you had m languages and n targets, you would end up with m times n compilers. So this is not really a scalable approach. And so compilers actually evolved this way. People realized that it would be better to actually separate out front ends and back ends. So you would have different front ends for the language. You would have a common intermediate representation, right? And you would take the language and then translate to this intermediate representation, apply a bunch of passes on this intermediate representation, optimize the code, and then you would have a different backend for each target. So this way, from m times n, you go to m plus n, or strictly speaking, m plus n plus 1. And more importantly, this approach is modular and reusable. You share infrastructure. So this is how compilers evolved, and this is how a modern compiler today looks like. LLVM, which is a low-level virtual machine, and it's been tremendously successful. And most of the languages and the things that you run on your phones, etc., have probably gone through LLVM, and the code that you run has gone through LLVM. So with C, C++, Go, Rust, also there are many other things that I haven't listed, like Haskell, Swift, Objective-C. All of these languages typically have different front ends. They are lowered to LLVM IR, which is the modular and reusable infrastructure, and this takes a target description. So it's even better than the m plus n in some sense. You have this common infrastructure. It takes a target description and is able to generate code for a number of different backends. And so it's been very successful. And a lot of companies as well as programmers have made a living by creating a new infrastructure on top of LLVM. Now, what's the connection of all this to this new domain of artificial intelligence and ML? So this problem that we've had with the compiler infrastructure, so this exists today. So we already have this today. But we have now a similar problem for AI and ML computation. There's been an explosion of different programming models for AI and ML. TensorFlow, these are all logos of these different programming models. TensorFlow, PyTorch, Keras, Swift for TensorFlow, and so on. And people are building new programming models. That's on the programmer side. So this is what faces the users. On the other side, there's an explosion in the number of specialized AI chips and accelerators that people are building all over the world that are specialized at certain tasks. They can accelerate certain kind of computation. And sort of there's a huge gap. So there are chip vendors who are asking what sort of software stack we should have, what kind of compiler infrastructure we need in order to support some of the well-known programming models on their hardware. Similarly, people who are developing new programming models or domain-specific models would like to know what sort of compiler infrastructure they need in order to be able to support all the different. And each of these models is actually, if you look at how things work today for TensorFlow, let's say, which is the dominant deep learning programming model, it has a very complex ecosystem. And so sort of this slide actually shows the amount of complexity that's inside TensorFlow. It's about 2.3 million lines of source code. And again, this complexity is undesirable. A lot of experts feel that there's a lot of replication, duplication. So for all the different targets that TensorFlow supports, CPUs, GPUs, Google's TPUs that are used on its cloud. There are different pieces of infrastructure, different intermediate representations that are used, and people replicating and duplicating optimization infrastructure all over the place. So this is a serious problem. Yeah. And so this is a serious problem that we face today. And so it would look like I'm suggesting that a startup should try to build some modular and reusable infrastructure. But again, that's not what I'm suggesting here, because that would involve a whole lot of expertise. It would involve a big team. It has to happen in the open source. It can't be commercially exploited. Fortunately, there's MLIR that Google recently open sourced, and that's sort of the base IR infrastructure that startups could use to build, whether it is support for their hardware or to support programming models. And so it was open sourced by Google in just a couple of months ago, and I happen to be one of the co-founders of this project. I spent a sabbatical at Google last year. And so this is really an infrastructure that is well suited to take high-level machine learning computations and generate efficient target code. One of the problems with LLVM is that it does not have any first-class concepts for multidimensional arrays and loopness, and these are the typical data structures that are used a lot in ML computations. Okay, so and finally, so I think this is where a lot of opportunity exists, and my startup is particularly building certain modular and reusable infrastructure on top of MLIR that allows progressive lowering from machine learning programming models to specialized accelerators. And one of the things that we have done a lot of research on is the polyhedral compiler framework, especially suitable whenever you have multidimensional arrays, basically auto-parallelization and optimization of computations that are rich in these data structures. And this is what we are trying to exploit. Okay, so thank you.